Okay, in this question we are doing a horizontal dilation. Now what type of horizontal dilation? Well, it could be a stretch, it could be a compress. What we're asked to do is we're asked to apply the scale factor of 1/8 to the function of y equals log x. Now I've already taken the liberty of drawing y equals log x. There it is there. It looks like that, cuts through 1, 0 and goes up very, very gently, gentle gradient along there. So that's our function, that's what it looks like. But what we're going to do is we're going to apply this 1/8. So what is this scale factor of 1/8? Well, basically all you have to know is that the scale factor affects a function horizontally from left to right along the x-plane. So it's either going to compress it and bring it closer to the y-axis, or alternatively, it's going to stretch it further away from the y-axis and closer to the x-axis. So we've got to ask ourselves, is this going to be a stretch or a compress? Well, it's really easy to deduce this because all you have to do is look at the scale factor. If the scale factor is between 0 and 1, like a fraction, the scale factor, if it's a fraction, it means that it's going to compress because it's going to be 1/8 the horizontal width or the narrowness or the wideness of the original function. It's going to be 1/8 as much. In other words, the original function will be 8 times wider. So that's what that tells us, right? Because it's a factor, it actually scales it. Now, how do you actually take this and apply it and create a new function? Well, all you have to do to create the new function is take the scale factor and divide it under the x. So all you have to do is replace the x with the scale factor. X over scale factor. So it works like this. Let me just write it out. So if we got y equals log x, that x will be replaced with x over the scale factor. So our x will still stay x over our scale factor, I'll write that in red, 1/8. That's all you do. X over the scale factor, x over the scale factor, like that. Now we can simplify that, and that means it's going to equal y equals log x, or 1x divided by an 1/8 is actually 8x. So there you go. So that is our new function. Y equals log 8x. So y equals log 8x is going to be drawn up here, and we're going to see that it's going to be more compressed by 1/8 as we represent it visually, so we can gain a better representation. So let me just draw a table of values, just a few points, so we can sketch it up here and actually see and gain more clarity into that log 8x. So we'll start off with the x value, and we'll write down log 8x. Log 8x. So we'll go, let's start at about 1/2. So we'll go 1/2, then we'll jump further to a 1, we'll go 2, let's jump to 4, then we'll go maybe 6 and then maybe 8. Just a few points. And we'll plot those points now. Okay, let's substitute 1/2 into log 8x. So that's going to replace the x, 1/2. 8 times 1/2 is 4, so log 4. What's log 4 going to be? You put it in your calculator, and that's going to give you a value of log 4 is 0.6. Okay, let's put in 1. Log 8. 1 times 8 is 8, so log 8 is going to give us in your calculator, log 8 will be about 0.9. Okay, let's go to 2. 2 times 8 is 16. Log 16 is about 1.2. Let's go to 4. 4 times 8 is 32. 32, log of 32 is 1.5 approximately. And 6. 6 times 8 is 48. Log of 48 is going to give me 1.7. And finally 8. 8 times 8 is 64. Log of 64 is 1.8. So it's rising very gently. Let me just put in the points. 1/2, 0.6. 1/2, 0.6 is there. 1.9. 1.9. We have 2, 1.2, 2, 1.2. We have 4, 1.5, 6, 1.7, and 8, 1.8. So if I join the dots on this, it's going to look something like this. There we go. That's what it looks like. Let me just write it in. Y equals log 8x. Log 8x. That's what it looks like, log 8x. So is it compressed? Well, yes, because this is closer to the y-axis than the original blue parent function. What else can we tell? How else can we tell that's compressed? I'm actually going to write it here. It's compressed, or squashed is another word. So it's closer to the y-axis, the other one's closer to the x-axis. So if we can pick a couple of points and see how much more it's compressed, there's no real points that's going through anything in particular. So if I was to pick, let's see here, we've got 1.9, about there, 1.9, if I put a point there, it's at about 0.9. So I want to go to the height of 0.9 because we're going along the same horizontal plane. So that goes at 1.9. And then if we go for the original one, the y equals log x, I want to find 0.9. 0.9 is at about 8, right here, right there. That's 8.9. So that's 1.9 on the same plane. It's just below the 1. It's like 0.9, sorry, just below. So if we look at these and we draw a line through, it's going to be a little bit lower than the 1. It's going to go through about there roughly. It's a little bit lower than 1 at 0.9. So along the same line, you can see that the original function is 8 units away. The new function is at the same place, the same line, 1 unit away. So clearly it's 1 unit out of 8. So yes, it is in fact 1/8 as wide on the same line as the original parent function.